In our discussion of the mind-body problem in earlier lectures, we found that, in effect, in order to solve this problem, we have to challenge some of the conceptual distinctions that Descartes and others were making. Basic to our whole tradition is the assumption that mental and physical name mutually exclusive categories. That if something is mental, it can't be physical. If it's physical, it can't be mental. And what we found was that those categories just aren't adequate to describe the facts as we know them. When we talk about the mind, we're talking about a feature of the brain, in the same way that when we talk about digestion, we're talking about a feature of the stomach and the digestive tract. We're just talking about a series of biological processes that go on like other biological processes. But that's difficult for us to say, given our tradition. And another feature of this tradition, one that's going to come up in this lecture, is the traditional contrast that we make between machines and nature. The idea is that if something is part of nature, it can't be a machine. If it's a machine, it can't be part of nature. And with that goes the question, can a machine think? And how are we to understand our thinking in relation to the possibility of machine thinking? Now, the Chinese room argument challenges the idea that a system can think solely in virtue of implementing a computer program. What it shows, I believe, is that implementing the computer program by itself couldn't guarantee consciousness or thought or intentionality. Just implementing a computer program isn't by itself sufficient. And we also saw that there are numbers of attempts to answer that argument. There are a series of attempts to answer the Chinese room argument, and I answered many of those. Of course, as I said, there are dozens, maybe hundreds of attacks on the Chinese room, and I won't try to deal with all of them. But I did try to deal with what I think are the most common and influential. But recently, there is another line of attack that I want to mention, and that's this. In the past decade or so, we have developed new types of computation. We've developed new sorts of computers and new sorts of computer programs that are closer to the operation of the human brain. They are consciously designed to try to imitate certain features of the brain. And indeed, the guys who do these things normally describe their systems as neuronally inspired. They think that what they're doing is more like neurons than the traditional computer. Now, in order to explain that, let me say a little bit about the distinction between these machines and the traditional computers. Traditional computers, and that's the kind you'd buy in a store today, are sometimes called von Neumann machines, after the great mathematician and logician and scientist John von Neumann, who effectively designed our present-day computer. Using Turing's basic mathematical and computational ideas, von Neumann simply showed how to put this into hardware. The von Neumann machine works by going through a series of discrete steps, one after the other, in the way that I described in earlier lectures. And the marvelous thing about contemporary computers is they do that very fast. I mean, several million steps per second. However, there are other types of machines that are sometimes called parallel machines, whereas the von Neumann machine operates serially with a series of steps going one right after another. It's now possible to build computer architectures that use a series of computational processes that work in parallel, that work simultaneously, and they interact with each other. Now, people who have thought about how the brain might work find these notions useful because they think, well, we might design computers and computer programs that are more like the operation of the brain. And these are variously called parallel distributed processing or neuronal net modeling, as sometimes called the new connectionism, or usually just connectionism. Now, there's subtle differences between those, but for our purposes, let's just call them, all of these, connectionist networks, connectionist computational networks. And just to make it clear what's going on in these networks, I've drawn a very simple connectionist network on the board. It is a characteristic of the connectionist network that it comes in different layers. Now, of course, an actual connectionist network would have many more layers than the 3 that I drew, and it would have many, many more connections than I've drawn. But the idea is that you have a series of input signals that come into an input layer, and they're processed through a series of hidden layers, and then finally they reach the output layer where the cognitive task that we assign to our computer either is successful or unsuccessful. And the idea is that the system receives these signals, and they will be in the form of symbols. They'll be in the form of numerical values. Let's say you might have an input here of 1, and an input here of 0, an input here of a half, an input here of -1. And then there are a series of connection strengths in the different connections between the nodes. And we're to think of these, again, as like neurons. Think of each of these as sort of a neuron, and then you have these axons and dendrites, and they connect at the synapses with other neurons. That it's not really much like a neuron, but it's certainly more like a neuron, more like a system of neurons than the traditional von Neumann machine. Now, the key to understanding the operation of the connectionist network is the connection strengths between the nodes, because the input signals are multiplied by the connection strengths and then summed at the next node. So if you had a connection strength of 1/2 and an input signal of 1, that would send a value of 1/2 to the next node. And that node will then take a summation of all of the different inputs that it got from its different connections and then send those out to the next layer in line. Now, it is an interesting system, and it can do various things that are hard to do on a von Neumann machine. I mean, the basic merit of it is it's just faster, because you've got all of these different things operating simultaneously. You've got these different channels operating simultaneously, whereas with a von Neumann machine, fast as it is, you've still got to go through a series of linear steps. All right, now, how these things actually operate cognitively, the reason they're so exciting to a lot of people is that they appear to learn in a way that it's very hard to get a von Neumann machine to learn. And the way you get them to learn is you have what's called a teacher. Now, that's another computer. And what the teacher does is it adjusts the connection strengths whenever it makes a mistake. So if you're doing face recognition, for example, and you take a bunch of numbers that you attach to somebody's face and another numbers to somebody else's face, and then you feed in those numbers, and then you get you get pictures of the face in odd situations, and eventually, if you adjust the connection strengths, you can get the network, you can get this whole system to print out recognitions of Joe's face as opposed to Sally's face as opposed to Bill's face. You can get the system, as they say, to recognize faces. Now, of course, it doesn't actually recognize faces, it's not actually conscious, but what it does is it processes a bunch of vectors, it processes a bunch of numerical values that we use to represent the faces. Okay, now the reason I have taken a few minutes to explain this is that a lot of people think, well, this is really the kind of computer system that is going to answer the Chinese room argument. With this kind of computer system, we don't have to worry about the limitations of the old von Neumann machines, and I have even heard people argue, notably Paul Churchland, that this is the secret of consciousness, that this is the kind of thing that will explain consciousness to us. Eventually, when we get connectionist networks that are big enough and complex enough and fast enough, they will actually be conscious. All right, now with that in mind, with this brief sketch of a simple Mickey Mouse version of a connectionist network, I want to ask the question, how does that relate to the argument we had earlier? Does this answer the Chinese room argument? Does this get us over the hump from syntax to semantics? Do we get semantic content out of this type of symbolic processing? It's an interesting feature of these discussions that there's very little effort or attention paid to the question, what exactly is supposed to be modeling what? That is, when you've got a model of something, you want to know, well, what are the features of the reality that the model is supposed to represent? Because, of course, we can make a diagram or a model of anything, and we want to know what features are actually duplicated by the model and what features are just represented or are symbolized or drawn by the model. And that question is not fully answered by the proponents of the connectionist model of cognition. So let me talk about it a little bit. Our question, to put it sharply, is this: does connectionism, do networks like this, as opposed to the von Neumann machine, do they answer the objections to computational theories of the mind that I presented in earlier lectures? Do they answer the objection made by the Chinese room argument? The fundamental objection is that you can't get from the syntax of the program to the actual semantics or mental contents of human minds just by more syntactical operations. That syntax by itself, just manipulating the Chinese symbols, doesn't teach you the meaning of any Chinese words. You don't understand Chinese just in virtue of carrying out the computer program for understanding Chinese. Now, our puzzle now is, can we answer that with the connectionist net? And the answer is, so far, no. We haven't got enough in the connectionist net to answer the Chinese room argument for the following reason. You remember what we found when we discussed Church's thesis, that any function that you can carry out algorithmically can be carried out by a Turing machine. Any computable function is Turing computable. But now we don't evade that. That's a mathematical result. We don't evade that with this type of network. We've still got that problem. And to put it in words of one syllable, anything you can do with these things, you can do with a traditional von Neumann machine, because a von Neumann machine is a Turing machine, and we know from Church's thesis that anything you can compute at all, you can compute on a Turing machine. So there's nothing in principle that these machines can do that you can't do on an ordinary von Neumann machine. It's just slower. You see, whereas this does all this simultaneously, it multiplies 1 times a half and then adds a whole lot of vectors here to get another output to the next layer in line. Well, on a von Neumann machine, you just have to do that one step at a time. First you do this multiplication, and then you do this multiplication, and then you do this multiplication, and then that multiplication, and then you add them up and do a next bunch of multiplications in line. In fact, in the early days of connectionism in Berkeley, we couldn't afford the connectionist machines. They're too expensive. I mean, they cost a couple $1 million a piece, whereas you could get good computers of the kind that we were using for less than $50,000. And what we did, in fact, was run the connectionist programs on traditional machines. It just took all night. You start at 2 in the morning, and then at 7 a.m. you got a huge pile of printout paper. So if we're talking computation, if we're talking about what is a computation and what is a computable function, these machines are no theoretical advance at all. They're just a different style of programming, and they work a lot faster. If the Chinese room argument shows that computation defined in terms of symbol manipulation is not by itself sufficient to guarantee cognition, then these machines are no advance whatever, because insofar as they're doing computation, the only difference between them and traditional machines is that they're much faster because they work with a whole series of computational processes operating simultaneously in parallel and interacting with each other. But of course, there's another way of interpreting these systems, and that is, well, let's think about the actual hardware, about the actual wires and the actual connections that go. Now, couldn't you get consciousness or intentionality or cognition as a kind of emergent property growing out of that? Couldn't you get kind of a glow of consciousness given off by this system, which is what the brain which is like what the brain does. Well, there's nothing in the Chinese room argument that answers those kinds of speculations. But now notice, when we say that, maybe by duplicating the formal structure of the brain in this particular type of wiring, you might get something that does what the brain does. That's a piece of neurobiological speculation, and the Chinese room argument doesn't defeat these speculations. The Chinese room argument just says computation by itself is not sufficient for cognition because computation is defined purely formally or syntactically. However, I think as a piece of neurobiological speculation, it's out of the question. I mean, anybody who knows anything about neurons knows that they're very specific. They have very specific neurochemistry. The neurotransmitters have a very specific effect, different for each transmitter, and they have very specific chemical structure to the neurotransmitters, and they affect the rate of firing of the neurons by very specific mechanisms. So, just to summarize this point, if the connectionist net is supposed to be thought of as computation, it makes no advance on the traditional von Neumann machine as far as the theory of computation is concerned, and it's as much subject to the Chinese room argument as any other computer system. If we're to think of it as not a piece of computing machinery, as a computational device, but as an attempt to build an artificial brain, then we're in the realm of speculative neurobiology. I think it's quite fantastic to suppose that you could do it with a bunch of wires, but that is a claim on my part about how the brain works and not a logical or philosophical or a priori argument. So I think we can safely say that if we're talking about the theory of computation, this does not meet the Chinese room argument. Now, I don't want to put these down. I think this is a good way to do models. It's a good way to do simulations of brain processes, and no doubt we'll get more useful results from these in the future. You remember implicit in our account of the Chinese room argument and its relation to theories of cognition is the distinction between strong AI and weak AI. Weak artificial intelligence just says you can use the computer to study the brain, and cognition in a way you can use the computer to study the weather or to study the flow of money in the economy or the behavior of cells undergoing mitosis. Now that seems to me a useful project. And it seems to me, in the end, though these connectionist nets don't meet the Chinese room argument, that does not mean that they're not useful as weak AI, as computational models of how brain processes might actually work to produce cognitive phenomena. All right, but now then, all of this discussion raises a much larger set of questions. Can a machine think? Well, this is an old chestnut of a question, and let's ponder it for a moment. The assumption behind the question is that there's some kind of contrast between us and machines. But it depends on what your definition of a machine is. If by machine you mean any physical system capable of performing certain functions, then there isn't any question that our brain is a machine. It is a biological machine, and it causes consciousness and intentionality by ordinary biological processes. So if our question is, can a machine think, then it's got a trivial answer. Of course, our brains are machines, and they can all think. But you have the feeling, well, that wasn't really what worried us. It wasn't, can our brains do it? We know they do it. But could you build an artifact? Could you build an artificial machine that could think? And there, it seems to me, there's no reason in principle to suppose we couldn't build a thinking machine, that we couldn't build an artificial brain. We're nowhere near being able to do it with our existing technology because we don't know how the brain does it. But there's no more obstacle in principle to building an artificial brain than there is to building an artificial heart. I mean, we found out how hearts do it. The heart's a pump. And then we built artificial hearts that can do what the heart can do. Now, as it's science fiction to suppose that we're going to do this for brains in our lifetime, but I don't see any theoretical obstacle to building an artificial brain that could have cognitive states exactly like our own. But now then, the next question one is inclined to ask is if you think, well, look, if it's in principle possible to build an artificial brain, maybe out of some other materials that could do what brains do, then why couldn't a computer? Why couldn't there be a computer that was an artificial brain and actually produced consciousness and other cognitive phenomena? And the answer to that is, as far as the argument so far has gone, there's no obstacle in principle to something being both a computer and being conscious. I mean, in a sense, whenever I compute, I am a computer. I add 2 plus 2 to get 4, and I am conscious. So there's no obstacle in principle to something being a thinking computer, because we are all thinkers and we're all computing. We all compute whenever we do addition or subtraction. But now people are often puzzled. They think, well, what did the Chinese room argument show then? Because if it's possible that there could be a thinking computer, I thought the Chinese room argument was supposed to show that computers can't think. Well, let's state this carefully. What the Chinese room argument showed is that computation is not sufficient to guarantee the presence of thinking or consciousness. It doesn't show that something couldn't be both a computer and be conscious. What it showed is that consciousness by itself is not constituted by symbol manipulations, that consciousness by itself isn't guaranteed just by having a bunch of zeros and ones. So we need to distinguish the question, can a computer think? And the answer to that is trivially yes, because we're all computers and we can all think. I mean, everything that thinks will have some description under which it is a computer. Therefore, it follows that some computers can think. But the question we were interested in is not, are there a bunch of machines, namely human beings, who can both compute and think? The question was, is computation by itself sufficient to guarantee the presence of thinking? The claim that I made was, if the theory of strong AI is necessarily what computes correctly thinks, I argued against that. No, that's not necessarily true, because something can compute Chinese correctly and still not understand Chinese. But what I did not argue was necessarily if something is a computer, it can't think. Rather, it's just not necessary that if it's a computer, it must be thinking. So the important point here to see is the modesty, really, of the claim advanced by the Chinese room argument. The claim is computation by itself is not sufficient to guarantee thinking. The claim is not that something couldn't both compute and think, because we all do that. We're all capable of both of those. All right, but now that raises what I think people will naturally want to know is the answer to the next question. Well, what do you need? What would you have to have in order to build a thinking machine? Well, let's remind ourselves of what we established when we discussed the mind-body problem in an earlier lecture. Now, remember, there were 3 steps to the original argument. 1, programs are syntactical. 2, minds have semantics or semantic content. And 3, the syntax by itself is not sufficient to guarantee the presence of the semantic content. Now, we saw from those 3 premises, it followed that programs aren't minds. Programs by themselves are not sufficient to guarantee mental contents. But now we added another premise. And that premise, you remember, was brains do it causally. We know as a matter of fact about how the world works that all of our conscious states are caused by lower level neuronal processes in the brain. But that fourth premise now itself has a simple logical consequence. It's a trivial logical consequence of the fact that brains do it causally, that any other system that did it causally would have to have causal powers equivalent to brains. If you're going to do it with some other kind of machinery, you've got to duplicate the power of the brain in that machinery. I want that to sound trivial. I want it to sound like an obvious consequence, because it is. It's a bit like saying, look, if you got a gas engine that'll drive your car 80 miles an hour, and you want to build a diesel engine that'll drive your car that fast, then you got to build a diesel engine with an equivalent power output. From the fact that the gas engine does it causally, then it follows trivially that any other system that does it causally has got to have an equivalent causal power. Now, that's exactly analogous to the claim I'm making now. From the fact that brains do it causally, we know that any other system would have to have causal powers equivalent to the brain. Okay, but now we've got some interesting results. I mean, you start off, it's typical of philosophy, you start off with some rather modest-looking things. Yeah, okay, programs are defined syntactically, minds have mental contents, but you start thinking about their logical consequences, and you get interesting results. From the fact that brains do it causally, we deduce that any other artifact, any artifact that did it causally, would have to have powers equivalent to brains, would have to have causal powers equivalent to brains. But we then tie that to our conclusion of the Chinese room argument, namely that programs aren't enough. Programs by itself wouldn't be enough. So by conjoining those two, we get the following result. Any artifact that could produce consciousness, any artifact that could produce intentionality, would have to do it by duplicating the causal powers of the brain, and no computer program is sufficient to do that because, for the reasons we gave earlier, the computer programs are defined purely formally or syntactically. All right, but furthermore, then we know that the explanation, if we're now looking to find a theory of how our brain does it, we know from the foregoing argument that the explanation of how our brains do it, the explanation that we're looking for in neurobiology, cannot be, oh, well, the brain is just running the right program. The brain's just implementing the program, because we've been seeing over and over, just implementing the program isn't going to be enough because the program has no causal powers. The program by itself is purely formal or abstract. The only causal feature of the program is the implementing medium. And remember, the program is defined in such a way that it's totally independent of the implementing medium. One and the same program can be implemented in an indefinite range of different hardwares. One and the same hardware can implement an indefinite range of programs. All right, then just to wind this part of our discussion down, just to put an end to this part of the discussion, we can say, what was wrong with the whole computational theory of the mind was it was profoundly anti-scientific. It was profoundly anti-biological. This is ironic because these guys came to us saying, look, this is a scientific view of the mind. At last we got a science of the mind. The brain's a digital computer and the mind's a computer program. But what we've discovered is it is the essence of science that it tries to figure out how the world works, and it tries to figure that out as a causal story about how the world works. But you can't do that with computational theories because computation doesn't name a causal process. The irony of the whole history of the computational attempt, to give a computational account of the mind, is it was an attempt to show that the brain was a machine and the mind was a machine process. But in the end, the computation doesn't name a machine process. The materialism of the computational theory isn't nearly materialistic enough, because computation doesn't name a material process in a way that consciousness, cognition, perception, and intentionality do name material biological processes. Now, I have frequently misunderstood in these arguments as advancing the view that only brains can have consciousness or only brains can think, and I don't advance that view. I mean, that seems to me, how far down the phylogenetic scale consciousness goes and whether or not you can build an artifact that is conscious, those seem to me interesting scientific questions. Furthermore, I'm not trying to prove that this machine is conscious or that machine is not conscious. Look, I can't prove to you that this thing isn't conscious. I don't think it is. But this object I'm holding in my hand, this marker, is conscious. I don't think it's conscious. I think it's out of the question. It's absurd. It's science fiction fantasy to suppose it might be conscious. But there's no philosophical proof that it's not conscious. What I am arguing, rather, is there is a philosophical proof that computation by itself can't be constitutive of consciousness or intentionality because of the point I made earlier. It's defined purely formally or syntactically. And biology has to be respected in its causal specificity. The important advances in biology, such as the germ theory of disease or the DNA theory of heredity, are about the causal mechanisms that actually produce certain effects. I think we can extend this argument if we imagine a little thought experiment of the sort that philosophers like to perform on themselves. I don't know who first thought of this. It's bound to occur to anybody who thinks long enough about these questions. Here's how it goes. Suppose my brain starts to decay. And let's suppose I'm losing my vision. And let's suppose the desperate doctors trying to figure out how to restore my vision try plugging in silicon chips back here in V1, back in the visual area 1, used to be called Brodmann area 17. It's the back of the brain. It's the striate cortex. And they start plugging in these silicon chips. Now, there are different possibilities, but one possibility, which we couldn't exclude on a priori grounds, is maybe it works. Maybe we find that my vision is restored when these neurosurgeons start wiring silicon chips into my visual cortex. Okay, but now comes the next step. You always get this next step in these examples. Suppose the brain continues to decay, and they continue to plug in more silicon chips. And anybody, if you've ever studied any philosophy, you know where this example ends. Eventually, my whole brain is replaced by silicon chips. So when I shake my head, I can feel the damn silicon chips rattling around inside. Now, what are the possibilities? Well, one possibility which we couldn't exclude on a priori grounds would be the optimistic possibility. Maybe it works. Maybe I have all of my cognitive capacities. I'm fully conscious. I have all my memories because the silicon chips are performing the job that the brain was doing. The silicon chips are capable of performing the functions that the brain was doing before it began to decay. That is a causal hypothesis. Again, this is science fiction, but I'm working out various logical possibilities. Now, that's the optimistic version, but here is a pessimistic version. It might turn out that my behavioral capacities are kept intact. I still give my lectures and drive my car and eat my meals, but I slowly sense the area of my consciousness shrinking as they replace my brain with silicon chips. So, for example, they hold up an object in front of me and they say, we're holding up something blue, tell us what you see. And I want to cry out, I want to shout, I can't see anything in here, I'm going blind. But I hear my voice say in a way that's totally out of my control, I see a blue plastic object. Okay, that's the less optimistic version of this thought experiment, because now what we've got is a situation where there's a break between my behavior and my mental states. My mental states are deteriorating, my behavior is kept intact, and then we imagine the most pessimistic version of this. Eventually, my consciousness shrinks to zero. I'm totally dead, but my behavior goes on absolutely normally. None of my friends know, none of my friends detect any difference. This is not a likely prospect, and it's not one I would welcome, but it's not something we could exclude on logical grounds alone. All right, now there's a third possibility which is also depressing, and that is my consciousness remains completely intact, but my behavior shrinks to zero. My behavior gradually decays to the point that I'm totally paralyzed, even though inside I have a 100% conscious life. Now that last frightening thought, that you could be completely conscious and not able to show it at all, that in fact is not science fiction. There are patients who have had this experience and live to tell about it, and one is horrified to think of the ones who didn't live to tell about it. There are versions of the Guillain-Barré syndrome, is the name of that, where the patient becomes paralyzed and is unable to show any form of response to stimulus, but has a complete, rich, conscious life. The patient is fully awake, fully aware, and the doctors think, well, we might as well pull a plug on this guy because he's obviously brain dead. And the patient is fully aware of this. The patient is unable to move at all. I mean, just the medulla keeps breathing going and so on. The basic body functions are kept going, but the patient has no capacity for voluntary behavior at all, and yet has a completely normal conscious life. Now, some of these patients have recovered, and they say how frightening it was to be unable to express their conscious states in any form of behavior. So we had three possibilities. One is the artificial brain works just fine and has both behavior, restores both behavior and mentation, conscious states, and other cognitive processes. That's the good view. But there are two other possibilities. One possibility is you might turn into a robot. You might be in a situation where your behavior was perfectly normal, but your brain had decayed, that you had no consciousness, and eventually you are in effect dead. You're totally without consciousness, even though your behavior is kept intact. And the third possibility is the case where the behavior goes to zero, you become totally paralyzed, but your consciousness is completely intact. Now, there are two morals that I want to draw from this entire discussion, from the entire from the discussion of the silicon brains. One moral is we need to stop thinking that somehow or other behavior is essentially tied to our mental states. It's not. There's a purely contingent causal connection between our cognitive processes and their expression in behavior. You could easily conceive, and in fact I've just imagined a case where you had the behavioral expression without the conscious processes. And secondly, we've got to remind ourselves that when we talk about the conscious processes, what we're talking about is a biological effect of certain underlying biological processes. And any system that was capable of producing consciousness would have to duplicate the causal powers of the brain to do that. All right, now what we've seen so far then in this lecture is a consideration of consciousness as it relates to the causal powers of the brain, consciousness and other cognitive processes such as intentionality. And what I've argued is that the connectionist networks make no further advance as far as computation is concerned on the von Neumann machine, though I don't deny their usefulness. In fact, I'm enthusiastic about their prospects in aiding us to do cognitive modeling and aiding us to do what I call weak AI. And then I went through the various possibilities of how we might interpret the question, can a machine think? And notice that just as in our earlier lecture, we had to challenge the basic assumption that there is a metaphysical contrast between the mind and the body, so in this lecture, we have seen we have to challenge the basic metaphysical assumption that there is a contrast between nature and machines. Many processes in nature are machine processes. That is to say, they're physical processes that perform certain physical functions. But now if we think about that, if we think about the fact that nature seems to perform these functions, and often they are like the functions that machines, as we traditionally think of them, perform, so that it seems perfectly legitimate to think of the brain as a kind of machine and the heart as a kind of machine. It was an enormously important discovery when we discovered that the heart functioned to pump blood. It was not known until Harvey discovered it. If we think about that, then it seems to me we're likely to ask ourselves, well, what is a function anyway? What is it for something to perform a function? And I want to conclude this lecture by introducing another distinction which I think is crucial for our subsequent investigation and crucial for the investigation of cognition generally, not just for these lectures, and it's this. We saw that the mind-body distinction was no good, and we saw that the nature-machine distinction was no good. But there is a distinction that I think is crucial, and it's important for our subsequent debate and for our subsequent discussions, and that's the distinction between how things are intrinsically and how things are relative to our interests. Many features of nature are completely intrinsic in the sense that they're totally independent of us as observers. Think of force, mass, gravitational attraction, and photosynthesis. But there are lots of other features of the world that only exist relative to our interests, relative to us as agents, designers, users, consumers, etc. Think, for example, of a knife. A knife has certain intrinsic properties that are not relative to observers. Has a certain mass, for example. It's attracted to the center of the earth in a way that's totally independent of observers. But that it is a knife, if we say it's a knife, we're now talking about the function that we use it to perform. So one and the same object has the observer-independent feature of having a certain mass, but it also has the observer-dependent feature of performing the function of a knife. Now that distinction, the distinction between the subject matter of natural sciences on the one hand, force, mass, gravitational attraction, photosynthesis, mitosis, those are intrinsic or observer-independent properties of the world. That needs to be distinguished from things like money, property, marriage, government, knives, bathtubs, and chairs, because all of those are only what they are because people assign a certain status and typically a certain function to them. It's not a matter of just of my opinion that this is a knife. It really is a knife. But its being a knife is not a feature of its physics. Rather, it's a feature to which it's a feature of the use to which we put the physics. So I want you to keep that distinction in mind, the distinction between those features of nature which are independent of us, observer-independent or intrinsic features, and that's force, mass, gravitation, and all the other subject matters of the natural sciences, keep that distinct from knives, chairs, bathtubs, cars, money, property, marriage, and government, because those, in a sense, only are what they are because of the use we put to them, the function we assign to them. And our crucial next questions are going to be, well, what about cognition? What about computation? What about consciousness? Are those features observer relative, or are they intrinsic?